exponential and logarithmic models. Our objective here, we want to use Desmos to create exponential or logarithmic functions that model data that exhibit rapid growth or decay, which is exponential, or slowing growth or decay, which is logarithmic. Okay? Now, let's remind ourselves. So exponential, if the plotted data exhibit rapid growth or decay, it's possible that an exponential function can be used to model the data. Desmos uses this, y tilde a times b to the x, and it will determine a and b, and thus the exponential equation of best fit. And we'll do an example of that. Okay, logarithmic. If the plotted data exhibit an initial rapid increase and then a slower and slower rate of growth, which is the most popular one. Starts off fast and then slows down like that. It's possible that a logarithmic function can be used to model the data. In these cases, Desmos uses this equation, if you will. I guess it's a modeling equation. Y tilde times a to the natural log of x plus c. It will determine the a and the c, and thus the logarithmic equation of best fit. So Desmos uses the natural log when it goes to model things, which of course we know is base e. Let's take a look at both. Okay, so example 1, the monthly premiums for a $250,000 term life insurance over a 10-year term period, well, they increase. They increase with age of the men who purchase it. So the older you get, okay, the premiums for the life insurance go up. The monthly premiums go up, of course, because you're more likely to die as you get older. The monthly premiums, and we're dealing with non-smoking males, are shown below. So at 35 years old, and you're looking for a $250,000 policy, and the monthly premiums over 10 years are $123 a month. If you go to 40 years old and you're looking for the same term life insurance, your monthly premiums have increased to $148. If you go to if you start at 45 years old, your monthly premiums have increased to $225, et cetera, et cetera. Obviously, again, look at this 75 years old. Okay, you're looking for life insurance. Well, the chance of a 75-year-old dying are far greater than the chance of a 35-year-old dying. And so that's why the monthly premiums are so much higher. Graph the data above with X as age and Y as monthly premium. Okay, let's do that. Give me a moment here. Let me get Desmos up and running. Okay, there we are. And we're going to add a table in here. So I'm going to do a plus, and I'll put a table in, and I'm putting my age, which is my X data, under the column of X1, and my ages are 35. They go by 5, so 35, 40, 45, 50, 55, 60. How high do I have to go? 75, 65, 70, and then 75. There we go. And I'll have my Y. Y is the monthly premium. At 35, the monthly premium was $123, and you can see my graph was set from before. Normally it's set like that, so I'll put it back. We can see the point come in. 40-year-old, the monthly premium is $148. A 45-year-old, the monthly premium is $225. For a 50-year-old, it's $338. Whoops. Put too many numbers in, $338. For a 55-year-old, it is $500. For a 60-year-old, it's now $783. For a 65-year-old, it's $1,330. For a 70-year-old, it's $2,448. And for a 75-year-old, it's a whopping $4,400. So there are my points. Now let's take a look. And obviously they're way up. I gotta get up this high on my y-axis. So let's see here. Let's move this over a little bit. I gotta do a lot of adjusting because I gotta get all the way to 4,400 and I'm only at 150. Well, there are some points coming into play. Again, I gotta get way up there. I gotta get up to 4,400. There we go. So I'm going from 0 to 80, which fits this just fine. And I'm going from 0 to 4,400. So we can see, and that has an increasing faster and faster feel to it, a look to it. That's an exponential look right there. And so let's ask Desmos to give us an exponential function that models these premiums. Okay, so we're going to go into here. Remind ourselves the model says y, but our data is in y1. So y1, y sub 1, excuse me, tilde. The tilde is over there. Okay. And then we have it a times b. So a, and then times b. The b is here. And we're going to raise that to the x power. Well, our x data is in x sub 1. So that's how our exponential model looks in Desmos, because our data is in x sub 1, y sub 1. Okay, and again, I say you want to check the log mode button. I don't recall exactly what it does. I'm not even sure I can explain it, but you want to check the log mode button. And I'm going to scroll down. I'm going to go down a little bit here. And it gives you what A and B are. Okay, A is 4.03891 and B is 1.09461. We'll go to 4 decimal places when we look at that and when we come up with ours. So let's move this over. And our model, letter B says create the model. Okay, y is equal to our A. Let's go back up to here. Our model has an A and a B, and Desmos, excuse me, Desmos told us that the A was 4.0389 to the 10,000th place, and that our B, the base, was 1.0946 raised to the x. So this is our exponential function that models these premiums, and Desmos gave us the two numbers we needed to put in there. Now I can do anything I want. I can graph this. I can give you a y, you can solve for x. I can give you an x, you can solve for y. I can give you any age I want, and you can come up with a premium using the model. I can give you any premium I want, and you can come up with the age using the model. We've done all that solving in previous videos. Okay, let's do an example with the logarithmic model. All right, so here's a logarithmic model. We'll see how the model, well, we'll take a look at the model. The table below contains the percent of the labor force that is female for selected years from 1940 projected to 2030. So in 1940, the percent that were female were 24.3%. In 1950, a little higher, 29.6%, etc., 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 up to 2030. Find a logarithmic function that models these data. Align the input to be the number of years after 1900. So this is going to be 40 years after 1900, 50 years after 1900, etc. So when we put it into our table, we're going to use 40, 50, 60 as opposed to the actual year. Okay, let's go do that. Back into Desmos. Okay, let's get out of these. I'll go back to the home screen here. Okay, set the table. Again, I'm back in X1, Y1 in this case. And let me get my, so 1940 is 40 years. So I'm going from 40, here's 50 years. After 1900, now this is 60, 70, 80. I'm just doing it vertically. Of course, you could do it back and forth, but I'm just doing it this way. 100, 110, 120, and 130 is 130 years after 1900, which is the year 2030. Okay, in 1940, the percent was 24.3%. In 1950, it was 29.6%. In 1960, 33.4%. In 1970, 38.1%. In 1980, 42.5%. In 1990, 45.2%. In the year 2000, 46.6%. In the year 2010, 47.9%. In the year 2020, 48.1%. And finally, in the year 2030, projected, 48.0%. Okay, if I look at my graph, well, I need to get my x's between 40 and 100, so I got to see those. There's my 40. Oops, a little bit too far. Between 40 and 130, that's pretty good. But my y is between 24 and 48, so I got to come in here. And there it is, right there. There we go. And we can see where the growth is going up, but it's slowing down. So I have kind of a logarithmic look here. A little faster early on, and then as time goes on, it's the growth of the percent of females in the workforce is slowing down. So it looks like that's a good logarithmic model. So let's put in our logarithmic for Desmos, which is y sub 1. Again, we're pulling the data from the column y sub 1. So Desmos says where we pull the data from, and it was from y sub 1, tilde. And then you put in the letter A, and then the natural log. Well, the natural log is under the functions. Scroll down till you see the natural log, which is right there. So natural log of x sub 1, because it wants to pull the x data from column x sub 1. Close your parentheses, then we're going to add a c. Okay, add c. And then again, check your log mode box. And you'll notice it's not bad. I mean, you notice your r squared is 0.96. That's really high, but it's not 0.99, but it's a good model. Let's take a look. If we scroll down here, they're telling us the A value to make this work is 21.729, and the C value for this log model is negative 54.775. So we'll round this one to the thousandth place because this is to the thousandth place. Do notice it's a little bit high here. It starts to get a little bit low here, kind of equals, and it gets high again. So it's not perfect, but it's not a bad model. Let's take a look at how it works for us. Okay, so let's see here. Letter A, find a logarithmic function that does it. Okay, so letter A says y is equal to, the A value is 21.729 times the natural log of x. Our C value was negative 54.775. Now note, one thing I want to note, you may see this in the switched form, so you'll also see this written with this part first, negative 54.775 plus 21.729 natural log of x. As we used to say when we were little kids, same. How you see it written doesn't matter. Desmos is doing it this way, but some textbooks will kind of do it that way, or some problems will do it that way. They're just switching the two things. Okay, so that is our x is our years after 1900, and y is the percent that are female. Letter B, let's use the model to estimate in what year the percent of women in the labor force reaches 50%. So, letter B, we want 50% to be y, and I will make use of this one. Why not? Doesn't matter. So I'll write the rest of this equation. Okay, now we need to Now we're back to firm ground. We know how to solve this. We want to isolate the log portion. Well, let's first add 54.775 to both sides. On the left, 104.775, and on the right, 21.729 times the natural log of x. So now let's divide both sides by 21.729. And as I mentioned several times, if you're going to approximate, go out at least 4 decimal places. So I put this into my calculator, and to 4 decimal places, the answer was 4.8219, and that equals the natural log of x. My log portion is isolated, so I want to get at the argument. I'm going to rewrite it in its inverse form, which is its exponential form. Let's remind ourselves there's an e, so e raised to the 4.8219 equals the argument, x. And my loop helps me. Base raised to exponent equals argument. So this can go into a calculator, and x turns out to be 124.2, which is the years after 1900, which means we're talking about the year 2025, because it's past 2024. We've got into the year 2025. Now, interestingly, we go up to here, and we can see that in 2025, we weren't at 50%. The model, it kind of dropped off. But let's remind ourselves, it's just a model, okay? It's not going to be perfect, but we use the model to approximate, and you can see here, it kind of, our model is saying right about here, but as we know, it didn't get to 50% yet. We had a drop down with 10 years later. So our model in this case doesn't reflect it very well. But again, it's a best fit model. It's not perfect. It's just giving you a sense of how things are according to the best model that you have. So there you have it. How to use Desmos, and let's go back and go back and confirm these, or let's go back and review these. The exponential model, y tilde a times b to the x, and the logarithmic model, y tilde a times the natural log of x plus c.